So I want you to picture three things that honestly seem completely unrelated.
Okay, I'm picturing them. What are they?
First, a termite mound.
Yeah.
But I don't want you to picture like a little dirt pile in a backyard.
Right.
I'm talking about one of those towering cathedral-scale structures out in the savannah. You know, the ones that stretch 10 meters into the sky?
Oh, yeah, the ones with passive air conditioning and specialized nurseries, fungal gardens, even.
Exactly.
Yeah.
Huge, complex structures. Okay, so that's the first thing. Second is the real-time routing of public transit in a dense, bustling metropolis.
Like Tokyo or New York.
Yeah, exactly.
Right.
And the third thing is the entirety of Wikipedia.
I mean, that is a genuinely bizarre lineup when you put them side by side.
Right.
You've got colonial insects, massive city infrastructure, and then the world's largest digital encyclopedia.
It sounds like a joke setup. But what if I told you that all three of those things actually operate on the exact same ancient coordination algorithm?
An algorithm that, frankly, biological nature perfected millions of years ago.
Yeah. And human beings are only just now realizing that it's secretly running our entire modern world. So our mission today on this deep dive is to shortcut your path to understanding this phenomenon.
Because once you see the mechanics of how this works, it fundamentally challenges everything we think we know.
Literally everything. How complex organizations are built, how they're managed, and how you interact with the world around you every single day.
And we have an incredibly rigorous stack of sources to guide us through this today.
Yes, we really do.
We're pulling from an extensive systematic literature review paper, a conference proposal, and a highly detailed slide deck.
All of this is the synthesized work of Dr. Marvin Starominsky-Uehara.
Right, from Temple University, Japan. And just to be clear for everyone listening, this is not just a theoretical thought experiment.
No, not at all.
Dr. Starominsky-Uehara conducted a massive systematic review. The initial sweep looked at over 12,000 sources.
12,000?
Yeah, spanning 9 different languages. And that massive pile was whittled down to 93 core papers across 5 vastly different academic disciplines.
So we are looking at hard cross-disciplinary data here on how a biological principle scales up to govern human society.
Exactly.
Okay, let's unpack this. To understand how a global network of humans actually gets anything done, we have to travel back in time to 1959.
And look at some bugs.
Look at some bugs, yeah.
Yeah.
Because there is a very strange word at the center of all this research. Stigmergy. Stigmergy.
Stigmergy.
Can you define what stigmergy actually is, like mechanically?
Sure.
Because as I was reading through these papers, I kept coming back to this analogy, and I want to know if I'm on the right track.
Let's hear it.
Is this basically like when you're walking across a massive snow-covered field?
Okay.
And instead of burning energy to carve your own path through the deep snow, you just step in the footprints of the person who walked ahead of you. And then the next person does the exact same thing, and the next, until suddenly there's a permanent packed down path in the snow that everyone just blindly follows.
That is exactly what is happening. Your analogy perfectly captures the mechanics of it.
Oh, awesome.
Yeah. The term stigmergy was first introduced in 1959 by a French scientist named Pierre-Paul Grasset.
Grasset, right.
He was studying how termites construct those incredibly complex nests you mentioned earlier.
Right, the cathedral mounds.
And what puzzled scientists for years was that these insects are virtually blind.
Wait, really? They're blind?
Essentially, yeah. And they clearly aren't holding planning meetings. I mean, there is no termite architect holding a blueprint directing the workers where to put the mud.
So how do they coordinate something that massive?
Well, Grasset realized they communicate indirectly. They do it by modifying their shared environment.
So the environment itself is the message.
Exactly.
But how does a termite actually leave that message? Like, what's the mechanism?
Mechanically, it works through chemical traces.
Right.
A termite drops a pellet of mud that is infused with a specific pheromone.
Okay.
That pheromone is what Dr. Starominsky-Uehara calls a metamark.
A metamark?
Right. It's an intentional or sometimes random trace left in the environment. So when the next termite wanders by, it detects that chemical metamark.
And that triggers something.
Yeah, the pheromone acts as a biological trigger. It literally compels the second termite to drop its own mud pellet right on top of the first one.
Adding fresh pheromones.
Adding fresh pheromone.
Which creates a positive feedback loop. The pile gets higher, the chemical signal gets stronger, and that just attracts more termites.
Precisely. And once the pile reaches a certain height, the pheromone gradient actually changes.
Oh, interesting.
And that new gradient triggers a totally new behavior. They stop building up and they start building horizontally to form an arch.
Wow.
So through those hyper-local individual reactions to the environment, highly complex, optimized collective behavior just emerges.
That's wild.
Which brings us to the core rule of stigmergy. And really, this is the paradigm shift of the whole paper. No leaders, no plans, no direct communication, only traces.
No leaders, no plans, only traces. That completely upends the traditional corporate org chart we are all so used to.
It really does.
So if you apply that to the snow analogy, the footprints are the metamark.
Yes, exactly. And the crucial mechanism here is that a metamark is a persistent communication channel.
Persistent meaning it sticks around.
Right, it outlasts the direct interaction. The person who left those footprints in the snow could be miles away.
Or even dead.
Or even dead. But their trace is still actively programming your behavior when you choose to step in it.
That is just, I mean, it's decentralized coordination in its absolute purest form.
It is.
But, you know, if stigmergy just applied to insects leaving chemical drops or humans looking for an easy walk in the snow, it'd just be a neat piece of trivia.
Sure.
But the sources we're looking at show that this algorithm is actually the foundational architecture of the modern world.
Yes, the human world.
So how does a biological concept map onto our highly technical, digital, and social lives? Like, if pheromones are the physical metamarks for ants, is a like button a digital pheromone?
What's fascinating here is how the research categorizes this evolution. The systematic review identifies 3 distinct flavors of metamarks.
Okay, what are they?
Physical, digital, and symbolic.
Physical, digital, symbolic. Got it.
And it maps these across 5 major disciplines: biology, computer science, urban systems, collective intelligence, and human-centric studies.
Okay, so that covers a lot of ground.
It does. So to answer your question, yes, a like button is absolutely a digital pheromone.
Huh.
But the paper points to Wikipedia as the ultimate digital stigmergic system.
Okay, let me challenge that slightly.
Go for it.
Because Wikipedia does have human moderators, right, and admins who oversee things. It isn't purely wild and decentralized.
That's a fair point. It has oversight,
Yeah.
but the core engine of its growth is entirely stigmergic.
How so?
Well, think about the mechanics of a Wikipedia page. When a user creates a page and leaves a citation-needed tag,
Oh, right.
or they leave a red hyperlink to a page that doesn't exist yet, that is literally a digital metamark.
I never thought about it like that.
Yeah, it is a trace left in the environment that signals to the next user, drop a piece of knowledge here.
Oh.
The knowledge naturally evolves through this massive decentralized process of reading a trace, adding to it, and modifying it.
That makes the citation needed tag the exact equivalent of the termite dropping a pheromone-laced mud pellet.
Exactly.
It's a trigger for the next worker.
Yes. And the computer science applications go much deeper than wikis, too. The paper heavily details decentralized autonomous organizations.
DAO.
Right, DAOs, which run on blockchain technology.
Right, but a blockchain doesn't have a physical environment. There's no dirt to leave a footprint in.
True, but in this context, the digital ledger is the environment.
Oh, okay.
A DAO operates without a central management team. Instead, it uses tokenized activity traces as metamarks.
So, meaning what exactly?
When a user executes a smart contract or moves capital, that transaction is permanently etched into the blockchain.
Right, it's public.
That immutable ledger entry is the digital trace. If a large number of users start moving tokens into a specific project, that creates a heavy trail.
Just like a deeply packed snow trail.
Exactly. The concentration of tokens signals to other users, and critically to automated trading algorithms, that there is consensus or value there.
Which prompts them to follow the trail.
I got it.
So they're coordinating millions of dollars entirely through reading and reacting to the state of the digital environment.
Yes.
Okay, so that covers the physical trails and the digital trails. What about the symbolic metamarks? That seems like a much squishier concept. Where do those show up?
Well, the paper found a massive prevalence of symbolic metamarks in human-centric studies, specifically in clinical healthcare settings.
Yeah, like clinical healthcare.
Yeah.
I would assume an operating room or a clinical ward relies entirely on highly rigid, direct verbal communication.
You would think so.
Like, you don't want a doctor leaving a vague trace when they need a nurse to administer medication.
No, you would certainly hope for direct communication, and healthcare professionals actually report a strong preference for verbal instruction.
That makes sense.
But the research data shows they pervasively use metamarks to coordinate, often without explicitly realizing it.
Really?
They intentionally modulate the physical environment, maybe by angling a patient's chart a certain way, or leaving a specific surgical instrument on a particular tray, or even marking a door frame.
So it's an invisible symbolic language.
Yes.
Why do that, though? Why not just say, hey, prep this instrument?
The mechanics of it serve a very specific social function. It promotes efficiency in a loud, chaotic environment, but crucially, it saves face.
Oh, saving face.
Right.
Right.
It allows a nurse to politely correct a senior doctor or suggest a course of action without having to initiate a potentially uncomfortable verbal confrontation.
Oh, I see. It's like leaving the empty coffee pot out on the counter so your coworker knows to brew a new batch. But with life or death stakes, you're prompting an action without having to have the awkward, hey, you forgot to make coffee conversation.
That's a great way to look at it. The environment acts as a buffer.
Wow.
Now, the interdisciplinary applications of this get even broader. The paper covers 29 subcategories.
79.
Yeah, and one of the most striking is geopolitics. Specifically, the research looks at the construction of border walls.
Okay, before we get into geopolitics and border walls, we need to be absolutely clear with you, the listener.
Yes, very important.
The sources we are unpacking today contain analyses of politically sensitive topics. We are not taking any sides here.
Right.
We are not endorsing any left-wing or right-wing viewpoints regarding immigration, national security, or international law. Our only goal is to impartially report on the content provided in Dr. Sturminski-O'Hara's research.
Simply trying to convey the ideas in the source material.
Exactly. We just want to explain how this biological framework is being applied academically to human systems.
A very important distinction. So, from a purely systems theory perspective, the paper frames a border wall as a massive stigmergic stimulus.
A stimulus.
Right. The research suggests that these territorial specifications literally act as environmental pheromones.
Environmental pheromones.
Yes, they guide entrepreneurial innovation between government actors and criminal organizations.
But how does a wall act as a pheromone? I mean, it's a barrier, not a trail.
Because building a wall fundamentally modifies the shared environment.
Oh, I see.
That physical modification leaves a massive trace. Mechanically, that trace triggers a behavioral adaptation from criminal organizations.
Like what?
Well, they might dig a tunnel or utilize drones to bypass it. And that adaptation leaves a new trace in the environment.
Which then triggers law enforcement to adapt their tactics.
Exactly.
Like maybe deploying seismic sensors to detect the tunnels.
Yes. It sparks an endless, decentralized feedback loop of environmental modification and reaction.
So neither side is directly coordinating with the other. But their behaviors are entirely locked together by the traces they leave in the environment.
Precisely.
Man, so if we are constantly reacting to the traces left by others, whether it's a Wikipedia page, a token on a blockchain, an angled medical chart, or a border wall, it forces an uncomfortable question.
What's that?
Are human beings really that much smarter than the termites? Or are we just using a highly complicated, resource-heavy version of their exact same algorithm?
Well, the raw data in the research definitely checks your ego on that one.
Here's where it gets really interesting. Because there is a specific data table in the presentation deck that maps this out.
The scale amplification table.
Yes, it compares the scale amplification of termites versus humans. And honestly, looking at the math, the insects are putting our entire civilization to shame.
It is a phenomenal comparison.
How?
Let's break down the mechanics of this scale. The paper measures stigmergic reach by looking at the size of the initial cue.
The metamark.
Right, the metamark, compared to the final built structure.
Right.
So for a termite, the smallest cue is a microscopic drop of pheromone. We measure that at the nanoscale, which is 10 to the power of -9 meters. But the structure they build, that towering cathedral mound, is 10 to the power of 1 meters, 10 meters tall.
So they go from a microscopic chemical drop to the equivalent of a 2-story building.
Yes. That is a biological leap of 9 to 11 orders of magnitude.
Unbelievable.
And the mechanics of this are vital to understand. They achieve that massive scale amplification with absolutely zero cognition. Zero centralized planning, and zero language. It is driven purely by localized environmental feedback.
Okay, and how do humans measure up on that table?
Well, for humans, our smallest cue could be a digital bit of data, which we also conceptualize around the nanoscale, 10 to the -9.
Okay, same starting point.
But the largest structure we have collectively created through these traces is the global internet, which spans roughly 10 to the power of 7 meters. So humans bridge about 16 orders of magnitude.
So 16 is bigger than 11. Humans technically win the scale game.
We bridge a larger absolute scale, yes. But look at the systemic cost.
The cost.
To achieve those 16 orders of magnitude, human beings require massive amounts of embedded culture.
Complex spoken and written language.
Massive legal institutions. Highly advanced technology, and frankly, unimaginable amounts of energy.
Right.
The source draws a really provocative conclusion here. Per unit of neural complexity, the termite ratio is actually far more efficient and impressive.
Ouch.
They do almost as much with a microscopic fraction of our brain power. It challenges the deeply held human assumption that sophisticated outcomes require sophisticated, intelligent agents.
That is the ultimate ego check. I mean, we think we are so brilliant with our strategic corporate retreats, our Slack channels, and our top-down sync meetings.
We do.
But maybe the most mathematically optimal way to build something complex is to just rely on environmental traces.
And we actually see this emergent optimality working beautifully in human systems when we let the algorithm take over.
Where do we see that?
The research points specifically to urban and transportation systems.
Like the transit routing we mentioned at the beginning.
Exactly.
How does a subway or a bus system use stigmergy? Because usually there is a central dispatcher with a very strict timetable, right?
Traditionally, yes. But the paper explores how transit networks that utilize environmental signals achieve better self-organizing performance than any top-down central planner could ever design.
Better performance? How?
Mechanically, it works by looking at the concentration of waiting passengers at a station.
Okay.
Instead of a central dispatcher blindly dictating that a bus must arrive every 10 minutes regardless of traffic, the transit vehicles adjust their headway distances.
The space between buses.
Right. They adjust that space based entirely on the stigmergic cues of the crowd.
Meaning the passengers standing on the platform are literally the metamark. Their physical presence in the environment is the trace that tells the system how to space itself out.
Precisely.
Yeah.
If a platform is crowded, it signals a delay, and the vehicles behind adjust their speed to maintain optimal spacing.
Without a human dispatcher ever intervening.
Exactly. The system dynamically regulates itself based on real-time environmental feedback.
That is incredible. But, wait, let me push back on this because it sounds almost too utopian.
Go on.
Nature's perfect algorithm, decentralized transit harmony.
Right.
If this entire system relies on us or an algorithm blindly following environmental traces, what happens when the environment itself is poisoned? Like, what happens when bad actors deliberately leave fake breadcrumbs? I'm thinking about, a swarm of fake bot-generated reviews on a product, tricking the algorithm and tricking consumers into buying garbage.
If we connect this to the bigger picture, you've just hit on the exact vulnerabilities that Dr. Stierminski-Ohara outlines in the paper.
Oh, really?
Because you're right, it isn't always a utopia. The paper dedicates a significant section to implementation challenges and the dark side of metamarks.
The dark side of the footprints in the snow. What happens when someone intentionally walks those footprints off a cliff?
Exactly. The first major vulnerability is deceptive metamarks.
Like the bot reviews.
Right. Digital platforms are highly susceptible to adversarial manipulation. In human systems, traces can be weaponized.
Weaponized traces?
When someone artificially inflates likes, deploys bot-generated product reviews, or executes a Sybil attack to manipulate a DAO's tokenized traces, they're using stigmergic principles for deception rather than cooperation.
Wow.
Mechanically, the trace is no longer an honest biological signal of optimal behavior. It becomes a trap.
Which completely breaks the trust of the system. I mean, the whole point of stigmergy is that we trust the trace to guide us to the easiest path.
Exactly.
If the trace lies, our collective intelligence instantly becomes collective stupidity.
It does. And the vulnerabilities get much deeper into ethical territory when the paper examines surveillance and autonomy.
Surveillance?
Yeah, the source material highlights smart homes as a prime example of what it calls spatial stigmergy.
Spatial stigmergy. But how does a house read a metamark? It doesn't have eyes to see where I left my coffee cup.
No, but it uses sensor activations and convolutional neural networks, or CNNs.
Okay, what is that?
A CNN is designed to process spatial data and recognize patterns. So, as you move through your house, sensors track your movement. The neural network encodes that data, turning your physical footsteps into a digital heat map.
Oh, wow.
You are leaving a continuous behavioral trace, and the CNN is the agent reading it, learning your schedule to optimize lighting or heating.
So my own living room is mapping my physical pheromone trail.
Yes.
That sounds incredibly invasive.
The paper raises massive questions about this.
Right.
Who ultimately owns those behavioral traces? If your environment is constantly reading your metamarks to anticipate your needs, at what point does optimization blur into perpetual surveillance?
That is a terrifying line to cross.
As human stigmergy shifts toward digital governance in smart cities, the consent around environmental trace collection remains a massive, unresolved issue in the research.
I mean, it's one thing when you're leaving temporary footprints in the snow.
Sure.
It's an entirely different reality when your smart fridge logs every single time you open the door at 2 a.m., encodes that trace into a database, and potentially sells it to your health insurance company.
Exactly. And the final vulnerability the paper addresses is coordination breakdown.
Coordination breakdown.
We tend to assume stigmergy only amplifies positive optimal behavior, like finding the fastest route for a bus.
Right.
But mechanically, stigmergy just amplifies whatever trace is left. It can just as easily amplify disorder.
Oh, I see.
The paper references the broken windows theory in urban settings to illustrate this.
Right, the criminological theory, where if a building has one broken window that is left unfixed, it sends a signal to vandals to break the rest of them.
Yes. In the language of this research, that visible neglect acts as a negative metamark.
A negative metamark.
It is a physical trace in the environment that signals to everyone walking by, no one cares about this space. There are no consequences here.
Wow. And because humans are stigmergic creatures, that trace guides subsequent behavior.
It amplifies antisocial activity and urban decay instead of harmony.
Right.
The environment is still communicating, the algorithm is still functioning perfectly, but the collective behavior that emerges is destructive.
So what does this all mean? We started today by talking about termites, Tokyo Transit Networks, and Wikipedia.
We did.
And by looking through the lens of this research, we've basically uncovered the hidden architecture of the world.
It's everywhere.
It really feels like we are in the middle of a massive paradigm shift. All our traditional hierarchical management theories, you know, the idea that you have to have a boss who tells the manager, who tells the worker exactly what to do.
Yeah.
They are being fundamentally challenged by this ancient decentralized algorithm.
Completely.
Stigmergy isn't just a bug thing. It is the blueprint for how we are building the next generation of smart cities, artificial intelligence, and our digital society.
It truly is a paradigm shift. The convergence of our biological instincts and our massive digital networks is creating what the researchers call the stigmergic society.
The stigmergic society.
We are scaling the termite mound to a planetary level.
And for anyone in like scientific or academic community listening to this deep dive right now, this conversation is just the beginning of the research.
Yes, there's a lot more happening.
Dr. Staraminsky-Ohara is actually guest editing a special issue on this exact topic for Interface Focus at the Royal Society.
That's right.
They are actively seeking cross-disciplinary articles exploring how metamarks and collective coordination span everything from the life sciences to our digital society.
It is an incredible opportunity to contribute to this emerging field.
Definitely check that out.
It's a brilliant framework to view the world through. And, you know, as we wrap up, I want to leave you with a completely different thought to mull over, looking toward the future.
Okay, lay it on us.
We've spent this time talking about how humans follow traces left by other humans, or how algorithms read human behavior.
Right.
But consider the rise of autonomous AI agents. Soon, we will have millions of AI programs crawling the web, executing tasks, and modifying the digital environment.
Oh, wow.
These non-human agents will inevitably start leaving digital metamarks for each other.
For each other.
Traces that are processed so quickly and written in code so complex that they are completely invisible and incomprehensible to human beings.
That's crazy to think about.
We might be on the verge of accidentally creating a secondary, invisible stigmergic society that runs the internet right under our noses.
Using the exact same algorithm the termites perfected millions of years ago.
Exactly.
An invisible termite mound built by AI. That is absolutely going to stick with me.
It's wild, isn't it?
It really is. Next time you are lost down a Wikipedia rabbit hole or standing on a crowded subway platform or just walking through the snow, look around at the traces you are following. Thank you so much for joining us on this deep dive. We'll see you next time.